Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for those students who've already gone through the substitution rule or the substitution method in Calculus 1 for integration. Now, after you've gone through that, there are some little tricks that should be very helpful for you as you move forward through calculus. So you might be watching this video at the end of your Calc 1 course, or maybe at the beginning of your Calc 2, or in the middle of your Calc 2 course, maybe after a teacher has told you that you should know these little tricks or something like that. The trick that I'm going to show you here involves integration when you have a function which only has a linear argument. So what do I mean by that? Well, suppose that you have this indefinite integral here, this integral of sine of 3x plus 1. We happen to know the antiderivative of the sine is the negative cosine. If you have just learned the substitution method or the substitution rule, you would do a u substitution here, allowing u to equal 3x plus 1, and then you would find the differential of both sides, or basically take the derivative of both sides. At this point, you would notice that the original integral does not have a 3 dx, instead it just has a regular old dx here. And so what we're going to do is isolate the dx here and trade it out for a du over 3. All said and done, everything is ready to go. We are going to go ahead and do our substitutions now. Now remember, dx is going to be traded out for a 1/3 du. I'll move the 1/3 out front just because that's a constant. Constant multiples can be pulled out front of integrals. And then we have the du, and we happen to know the antiderivative of the sine itself is going to be a negative cosine. And of course, remember, indefinite integrals require us to have a constant of integration at the end. Now, that u is not the world in which we started. We started in the world of x's. This answer is in the world of u. Again, let me say that. We started in the world of x, and our final answer is actually not in that world. It's in the world of u. So what we need to do is resubstitute in. This is very critical. We have to resubstitute in at the very end and to find out what the actual answer is in terms of x's. And there you have it. We have our final answer there. The integral of sine of 3x plus 1 dx is equal to a negative 1/3 cosine of 3x plus 1, then plus some constant of integration c. Now the trick here is that this is a function that we know the regular antiderivative for. When I say this, I mean the sine function right here. We happen to know the antiderivative of the sine. What is causing us to use a u substitution is that linear argument, the 3x plus 1. Now I'm going to show you the trick, and then I'm going to prove the trick to you. The trick goes like this. If somebody says, I have got the integral of sine of 3x plus 1 dx, you would say, well, that's very close to the integral of the regular old sine. And I know the antiderivative of a regular old sine is a negative cosine of its argument. However, that argument right there is actually being multiplied by 3. And the antiderivative of our original function, well, again, its argument is also being multiplied by 3. And when you take the antiderivative, you're going to do the opposite of multiplication to the antiderivative. The opposite of multiplication is division. So you're going to divide our final answer there by 3 to get the following. Now, if that was too fast for you, let me do it in several other situations. So let's say that we have the integral of 1 over negative 5x plus 4 dx. Now that is very roughly just 1 over x. It's not exactly, but it is roughly 1 over x. So what we want to do is take the antiderivative of 1 over x, which we all know is the natural log of the absolute value of normally x, and then plus c. However, that stuff that's inside the natural log, the argument of the natural log, well, that's going to be a negative 5 5x, in fact, let me color code this, 5x, and then plus 4. Notice x is being multiplied by a negative 5. So the antiderivative will be divided by a negative 5. Or in other words, you'll have a negative 1/5 out front. You can always double check the mathematics here by taking the derivative of the right-hand side. I promise you, it'll become the integrand, basically the argument for the integral. So pretty cool trick so far. You might be asking yourself, well, what if that number is not multiplying x, but instead dividing x? Well, the trick here still works. Let's suppose that we have the integral of the secant of 1/2 x plus pi times tangent of 1/2 x plus pi dx. Now we happen to know the antiderivative of secant of an argument, tangent of an argument, is actually the secant. The derivative of the secant is the secant tangent. So we know that this should come out to be something like the secant of that argument, 1/2 x plus pi. Kind of an important note here is that the arguments for this specific case have to be identical, right? That should make sense to you. All right, so we almost have it done. Remember, the argument, which is the x value here, is being divided by 2, or you could also say multiplied by 1/2. So do the opposite of multiplication by 1/2 to the antiderivative. The opposite of multiplication by 1/2 is multiplication by 2. So I'll just multiply the coefficient here, or put a coefficient of 2, and that will be the complete antiderivative. You could do this all day long as the arguments of your functions here are linear. Notice all of these are linear functions. They're not 1/2 x squared plus x plus pi or something like that. It's just 1/2 x plus pi. So let's go ahead and prove that this is the case. And in so doing, allowing you to use this trick from that point forward. Now, to be very honest with you, I've never done this as a proof. I've actually never done this at all, but kind of fun to do things you haven't done before on a video for the very first time. Why not, right? So we're going to do something like this. We're going to let capital F be an antiderivative of little f. Well, what does that mean? It means that capital F prime is equal to little f. It also means that if we would take the integral of little f of x dx, that should equal capital F of x and then plus some constant of integration. So far, I hope that you would agree with all of this, very logical, clean statements that you know from the fundamental theorem of calculus and doing your integration work already in your calculus course. Not a big deal. But here comes the big question. What about the integral of, instead of f of x, what about f of mx plus b? In other words, a linear function. Like, how does that antiderivative change? Well, we're going to do the substitution rule here. We're going to let u equal mx plus b, take the differential of both sides. Remember, on the right-hand side, the derivative of mx plus b is a constant, so the derivative of a constant is 0. The derivative of mx is just m, and of course it's a differential, so you have that dx hanging out. Now, if you take a look at our original integral here, this guy right here, the dx has nothing else attached to it other than the function. So there's no m dx there, so I'm going to go ahead and rewrite this differential notation with a 1 over m du is equal to dx. And now I'm going to do a clean sub, right? Dx will be traded out for a 1 over m du, and that mx plus b will be traded out for a u. So let's go ahead and do that. Let me slide down here. The integral of little f of mx plus b dx is now rewritten as, remember, dx is going to be traded out for a 1 over m du, and f of mx plus b is now f of the variable u. Now we happen to know the antiderivative of a function of a variable, and by the way, u is just a picture. It's just a variable stand-in. You can think of it as x, and we happen to know, we started with the assumption that capital F is an antiderivative of little f, therefore whenever we integrate f of a variable d variable, that should be capital F of the same variable plus some constant c. So the integral of f of u du should be equal to capital F of u plus c. Let me go ahead and write that in down here. Again, zoom in here because I'm running out of space. 1 over m integral, whoops, that's not integral anymore. I'm going to put it this way, times a group. Remember that integral of little f of u du is going to trade out for a capital F of u plus some constant of integration. I'll call that c sub 0 for a very specific reason. And then what we're going to do is distribute the 1 over m through. Now I've run out of page here, so I'm going to go ahead and distribute to the right. I'll have 1 over m, capital F of u, but u is mx plus b, plus 1 over m times a constant. Well, what's a constant times a constant, but just another constant? So I'm just going to go ahead and write that as the constant c. I've used c naught as a stand-in until I've finally glued together 1 over m and that c naught. That's a kind of an inconsequential little move, but there you have it. Now notice, if I'm going to integrate little f at a linear function, the answer is the same antiderivative at that same little function, but the coefficient of that antiderivative is the reciprocal of the coefficient of x. Now compare that to what we just did. All the way up here, the integral of 3x plus 1. Well, the antiderivative of, the integral sign of 3x plus 1. The antiderivative of the sign is the negative cosine. There it is right there to your right. And we have the 3x plus 1. But we're going to multiply that result by the reciprocal of 3, which is 1/3. Remember, the negative comes from just the antiderivative of the sign itself. Also, look at the integral of 1 over the negative 5x plus 4. That's a linear function down there. That's like an integral of 1 over x, which normally would be the natural log absolute value of that argument x, which in this case is negative 5x plus 4. And notice the coefficient here is a negative 1 over 5. Right? I made that choice because it's the reciprocal of the coefficient of x here. And likewise, we have that same argument for the antiderivative of the secant of 1/2 x plus pi tangent of 1/2 x plus pi. It's just going to be 2, because that's the reciprocal of 1/2, times the secant of 1/2 x plus pi. This little trick can pay you dividends in the long run because you're going to be doing a lot, and I mean really a lot, of integrations that involve functions you can normally take antiderivatives of, but they have linear arguments. Now I do want to warn you, this shortcut only works if the argument is a linear function. It will not work if it's a quadratic function or a cubic or some other type of function. So do not just immediately say, oh, for example, the integral of 1 over 3x squared plus x plus 2 dx. That, I'm going to just tell you right now, that's not the natural log of the absolute value of 3x squared plus x plus 2 times the reciprocal, or plus e, times the reciprocal of something there. That is not true. I don't even know how you could go about thinking of it that way, so my brain won't even allow me to go further with that example. However, you can now do a bunch of different antiderivatives. If somebody said, hey, I want you to take the integral of e to the 1/10 x plus 2 dx, you say, well, I happen to know the antiderivative of e to a power is just e to the same power, and the reciprocal of that coefficient is 10. There you go. That's all you need to do, very fast. So this, I hope, is going to be a very powerful trick for you. I don't like teaching tricks normally in any math course. However, this ends up being a skill that gets used quite a bit as you move through calculus, so you might as well just get used to doing it now. All right, I hope this video is helpful and you have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over obstacles getting in our way cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.